Let us discuss another topic, which is two classes of superconductors, type 1 and type 2 superconductors. The superconductors are classified into type 1 and type 2 based on the way in which they are transferred from the superconducting state to the normal state by the application of a magnetic field. There are here you can see two graphs. The first graph is for type 1 superconductor and the second one is for the type 2 superconductor. In both the graphs, the magnetizing field H is taken along the x-axis and the intensity of magnetization M is taken along the y-axis. Here you can see that M is given as minus M, because in the case of a diamagnetic material like a superconductor, the magnetic field M, that is the intensity of magnetization M, always opposes the applied field. Intensity of magnetization is the magnetic field developed within the material by when we apply another magnetic field, an external field to the material. Now the first graph you can see that when the field H increases, the applied field H increases, the M also increases up to certain point, and when it reaches to a maximum height, you can see that M suddenly reduces to 0. At that point the critical field is Hc. So that this type of material are called type 1 material. In type 1 material, initially the applied field is equally opposed by the magnetic field developed within the material, that is the intensity of magnetization, and when it reaches Hc, the intensity of magnetization suddenly falls to 0. That means there is no opposition to the applied field, so the applied field or the external field will equally passed through the material, that is the material become a normal conductor. Now in the case of the type 2 material, here you can see that up to the field Hc1, it is the curve, the graph is similar to that of type 1, that is H is equally opposed by M, but when it reaches the applied field reaches Hc, the value of M gradually began to decrease, which shows that the opposition to the applied field gradually decreases. Then the M becomes 0 at a higher field Hc2. So between Hc1 and Hc2, the material is a mixture of the normal conductors and the superconductor. That is, within the material there will be some layers will be normal state, which allows the magnetic field to pass through it, and some other layers will be in the superconducting state. This state is called mixed state or vortex state. So the graph shows that on the first part it is in a superconducting state, it is like normal conductor, so like type 1 conductor up to Hc1. Between Hc1 and Hc2, the material is in a mixed state, that is vortex state, and beyond Hc2 it is in the normal state. Now let us compare the type 1 superconductor with the type 2 superconductor. It is an important question for in the examination point of view. The type 1 superconductor is called soft superconductors. Soft in the sense that only a low magnetic field is required to change it into the normal state. Whereas type 2 superconductors are called hard superconductors. That is, a large critical field is required to change into its normal state. Then the second point is also the same, soft and hard superconductor. Then third point is, for a type 1 superconductor there is only one critical field exists, but for a type 2 superconductor there is a Hc1 and Hc2, two critical field exist. One is called Hc1 is called lower critical field and Hc2 is called upper critical field. Then for type 1 superconductor the critical field required is very low, whereas type 2 superconductor can withstand large critical field. Then type 1 superconductor exhibit perfect diamagnetism, perfect Mason effect. That is, the complete field lines are expelled out of the material when the field reaches Hc1 at superconductivity. But in the type 2 superconductors are not perfectly diamagnetic. That is, there is a mixed state. Then the current flow through a type 1 superconductor is only through the surface, whereas for the type 2 superconductor the current flows within the body of the material. For type 1 superconductor has only limited application because of the low critical field, that is even a small field can make it a normal conductor, but type 2 superconductors have a lot of practical applications because we can withstand a large critical field. Here you have examples for type 1 and type 2 superconductors. Now, an important quantum mechanical theory regarding superconductivity, which is called BCS theory of superconductivity. This is BCS means Bardeen, Cooper, and Scherfer theory of superconductivity. Three scientists, Bardeen, Cooper, and Scherfer, proposed a quantum mechanical theory for superconductivity, and this theory is called BCS theory of superconductivity. It is based on a concept called Cooper pairs. Cooper pairs means a pair of two electrons in an attractive configuration, and Bardeen, Cooper, and Scherfer BCS theory says that within a superconducting materials, electrons are forms pairs called Cooper pairs, and this Cooper pairs is like a liquid, that is it can flow within the body of the material without any resistance. This fluid or the sea of electron, the fluid of electrons within the body of the material is called superfluid. Here a Cooper pair is the name given to electrons that are bound together in a certain manner. First it was suggested by Leon Cooper, and here you have in this figure you can see the how a Cooper pair act as a Cooper pair is formed. This is a lattice of a metal, where lattice, this black dots represents the positive core atoms of the lattice, and this pink dot represents electrons. 1 and 2 are the electrons. So when an electron comes near a lattice point, you can see that the lattices get distorted because has positive charge and electron has negative charge. So there is an attractive force. This attractive force will distort the lattice. Now, when another electron 2 comes near this distorted lattice, it is also get attracted to positive charge core atoms of the lattice. So it is also get an attractive force. So here we have two forces. One is the repulsive force between 2 and 1, the two electrons. Second one is the attractive force between the electrons and the lattice. If the repulsive force between the electrons is just cancelled by the attractive force between the electron and lattice, then the net force will be 0. So these two electrons at low temperature will settle to a distance so that the net force experienced by the electrons is 0. So they will form a group of two electrons which is called Cooper pair. For the suggestion of this concept of Cooper pair, this Leon Cooper has shared Nobel Prize in 1972. Now here there is a diagram regarding the how these Cooper pairs are attracted to lattice and attracted to each other. In this diagram you can see that K represents an electron. K is actually the wave vector. Electrons are considered as wave having a wave vector K. So when an electron comes to a lattice point, K comes to a lattice point, it will emit a phonon. Phonon is the exchange particle in the case of the Cooper pairs. So Q is a phonon. A phonon is emitted by the wave vector, that is the electron K, and then it proceeds with K minus Q. This phonon is collected by the lattice, and another electron K dash come to this lattice point, accept this phonon, and it proceeds like a K dash plus Q. So the phonon lost by one electron is accepted by the another electron through a lattice point. This mutual exchange takes place, and thereby they will forms a Cooper pair. Now the high temperature superconductivity. High temperature superconductors. High temperature superconductivity means any material, any superconductor whose transition temperature is above 77 Kelvin. 77 Kelvin uh, is the temperature of liquid nitrogen. So if any material which acts as a superconductor within a liquid nitrogen, that is at 77 Kelvin, above 77 Kelvin, is called high temperature superconductor, and any material which has a transition temperature of 4.2 Kelvin. 4.2 Kelvin means the temperature of liquid helium. Below to 4.2 Kelvin, the material is called low temperature superconductors. Some examples are also given below. The pure metals are low temperature superconductors like titanium, vanadium, zircon, iridium, etc. But the alloys, compounds, most of the alloys and compounds will act as high temperature superconductors. Now finally the application of superconductivity. One of the important application of, there are lot of very high end applications to superconductors. One of the important application of the superconductivity is magnetic levitation or maglev, which is the idea of a high speed transportation system, which is the idea of superconducting trains which can be operated at a speed as high as 500 km per hour. It is actually practically done in Japan. There are a levitation means something that is gets suspended in air, that is floating in air. In the case of superconductor, because of its diamagnetic property, a superconducting material can be made to float in a magnetic field. That is because of the repulsive force. If you place a superconductor or superconducting material over a bar magnet, the superconducting materials will be float over the bar magnet because of this repulsive force. Now there are two different methods by which you can make a high-speed transportation system. One is based on electromagnetic suspension and second one is electrodynamic suspension. In an electromagnetic suspension, the electromagnets are installed on the train bogies, attract the iron rails. The magnetic wrap around the iron and the attractive upward force is lift the train. In electrodynamic suspension, levitation is achieved by creating repulsive force between the train and guideways, that is the rails. Now, other applications involves we can make powerful magnets, electromagnets by using the superconducting materials. Then in magnetic resonance imaging system, MRI scan, we are using superconducting magnets to produce high magnetic field as high as 13 Tesla. The nuclear magnetic resonance machines uses superconducting magnets. Then superconducting generators has the benefit of small size, low energy consumption than the conventional generators. So if we replace the conventional generators with the superconducting magnets, we will be able to produce miniature size generators having large capacity. Then fast and accurate computers, that is switching devices, can be constructed by using the superconductors. Then if we replace the power lines of our power lines with the superconducting wires, the requirement for this power stations, transformers, etc. will be eliminated. That is, you can directly transfer the power from the power stations to household because there is no loss of energy. So other applications are RF and microwave filters, then high sensitivity particle detectors, then rail gun and gun magnets, electric motors and generators, all these things. Then thank you for your patient hearing. I hope you have enjoyed my lecture. Thank you very much.